So, I'm Borislav Rizov, and I'm going to talk about Worldnet and our approach to Wordnet. And for one system that is in development for last maybe 15 years, and this is a third version of this. And of course, it's the most advanced and modern one. So this is the outline of my talk. I'm not going to teach you what is Wordnet, but I would like to give our point of view of Wordnet as a cryptic frame. This is a notion that is taken from the mathematical logic, and this is a very productive approach. Then I'll give you an introduction to Hydra and then go to this dynamic model that is the goal of this paper to be introduced. And we will introduce you our query language that is quite powerful and with which you can search the database. And the new approach is there in this dynamic language for Wordnet. And we'll finish with the implementation and the future goals. So let's start basically with what is Wordnet. It's, of course, it's some relational model of the language. What we have there is the words are organized in synonymous sets. And there are more than 20 semantic relations and some syntactic relations. And the most important one is the hypernym relation that is used to make some hierarchy and to that is somehow defined for all the languages in a similar way. Worldnet started, as far as I know, with the English Wordnet in Princeton. And its development continued for more than 40 languages. And it's still in development, and some are considered as finished, some are not. In most of the cases, it's used this synchronous model, but as Professor Persson mentioned, there are other approaches like merge, when you create your own structure and then map it to the other languages. And in most of the cases, this structure that the creators of the synthetic structures they follow the Princeton structure. And there is something like we call interlingual index, with which we map synsets that share common notion from different languages. It could be some relation or identifier. Most of the cases that is an identifier. Like, for example, English-Bulgarian pair is mapped by something like that. So, but this introduces several problems, like these Wordnets are monolingual. So they are developed in different teams in different formats, like files. Some use files, some use electronic tables, some use databases. And they are stored in separate places. And from time to time, there are some initiatives to map from one language to another to create some mappings. And because this, we have a problem with, for instance, the Princeton Wordnet does not have stable identifiers of the Wordnets. They are changed from version to version. That's quite problematic, and the people developed many algorithms to make mapping of automatic or semi-automatic methods to map scene sets from different languages. So to overcome this, some initiative called Chile was developed that is collaborative interlingual index. But in my opinion, it did not succeed and even made the things worse. They store the mappings in a public domain, but for particular versions of the particular language Wordnet. And that's not very useful at all. So let's start to show you our approach. We'll start with something that we call static model. What is static model is something like for some particular time, what we have is these scene sets and the relations, of course, so nothing new here. But let's start with this. We have some information that is somehow in the data. For instance, in the scene sets, such information is like part of speech or the base concept hierarchy, not a hierarchy, but clusterization identifier like first or second. And if we die in the scene sets, what we have is words. And we'll call these words that are in particular scene set literals. Keep in mind that one word can be in several scene sets. So for a particular scene set, we'll call this literal. So literal is something like a pair scene set and a word or a compound. And we have some text data like usage examples. We call these notes or just some features of something like the verb types. And let me change a little bit this approach. Let's think of these scene sets not as a set, but as an object, that is simple object. And the literals are object the same as the scene sets are. And what makes the scene set a set is a relation that connects the literals with the parent scene sets. So we have several literals that point to the scene set that these literals are part of. And in the same way, these nodes that are in the scene sets or the usage examples or some nodes in the literals can be associated with a particular object like literal or scene set with another relation like usage or another, let's say the relation is the relation that connects scene sets that are with that represent the same notion but are in different languages. This is this ILI relation, interlingual index, and etc. And in this way we receive a classical notion of cryptic frame that is a pair of objects and which have three classes: scene sets, literals, and nodes. And we have several binary relations like hypernymy, meronymy, or some let's say system relations like literal or interlingual index. And this approach was implemented in the system Hydra. Its development started 2006. And Worldnet was represented as a cryptic frame. It had model language, query language, which was quite powerful and useful. And it has the ability to contain several languages simultaneously. So we try to break this thing that the synthets are monolingual, but in the system to have all the languages. And the second version was developed maybe 10 years later. It was developed as a web single page application. And this system is available in production on this address on the site of the Department of Computational Linguistics of the Bulgarian Academy of Sciences. You see the address, and there are in the database 22 languages, and you can activate all of them, but let me tell you that by default are activated Bulgarian, English, and Romanian. But by means of the user interface, you can start French or Spanish, Finnish, etc. What is in the core of this system is this model logic query language. For this particular version, it's somehow hidden. So it uses this, but the user can search by means of a word or a compound or a regular expression. So what is a dynamic model for Wordnet? What we want to achieve. Over time, both the language and the Wordnet for a particular language is evolving. And this means that for any moment of time, we have some different state of the Wordnet database. And if we take a snapshot of the Wordnet of these static models in every moment, we will receive let's say a list of Kripke frames in the way that I described these static models. So if we make the union of them, if we consider these static models to be disjoint from each other, we will receive a big Kripke structure, Kripke frame that have a static model for every single moment of time. So somehow we have all of the version of all of the data and all of the instances of the relations in one database. So we may think of the time as a discrete one. Our approach is this way. Every change in the database introduces a new moment of this discrete time. So if you take a time for the usual notion of time, a moment, let's say timestamp, there is one moment that is the nearest one from this discrete model. So we can consider this like mapping of the usual time to this model time. And another thing that somehow is clear, that we have this feature that only one object is changed in one model time. So for a moment, we have all instances of the static model with the most recent version of the object. So we have something like this. We have several versions of one object, several versions of another. And when we get some moment of time, we can take this version that is the nearest previous moment to this moment. And in this way, we receive the static model that is for this particular moment from the global structure that is with all the moments, let's say. And this collection of static model is this dynamic model. So we have query language that was introduced from the very beginning. This is a model logic language, and now it is enhanced with several time modifiers. And because there are a lot of problems that arise when people are developing Wordnet. There are some inconsistencies in the database, and there are questions about who exactly made this problem and when it was introduced. So one approach is to revert to some previous state, but you're not sure how to fix the system, what data you should preserve from one version to another, and who did the problem. And with our approach, we solve these problems. And we want to make this without reverting the data, but to have all of the data available at any moment. For searching, we use something that is called model checking. So when you say, I want this query, what you receive from the system is the object in which this query is true. I'll show you an example in a minute. So we have something like constants in the language. These are the atomic formulae. We have some identifiers for every object. We have some constants, like we call them constants, but it's something like this format type value. For example, you can search for nouns like this. You say pos and n. That's it. And this particular query will find you the scene sets that are nouns. And of course, we have the set of relations. They are used like modalities. We'll see in the examples. And we have 4 types of temporal modifiers implemented. These are for concrete timestamp. This is for this model time. So this is exactly the operation 1, 2, 3, 5 in the database. So in this moment, the database have received 1,235 operations, so some modifications. This means that you want from the particular moment that you start your query 5 days later, and of course, we don't see the future, but we can ask the system something like, I want 5 days ago something to be true, and 3 days later something new to be true. And that's the reason we have this future thing. And P3 says that this is 3 days ago. So we have something like bottom that is never true, something, this is top that is every time true, and these constants are atomic formula. And the formulas are in the usual way introduced as by an induction. We have negation, conjunction, disjunction, implication, equivalence. This is the usual model operator diamond of the relation R and the square, and this is time modifier, which in the system is again like a model operator. And we have some modifiers of the relations that are quite useful, like the reverse operation or the transitive closure or the transitive and reflexive closure of the relation. And this is the semantic, but I think I don't have time to put it. But it's not very complicated thing. This is defined for some particular time. And when we say some formula is true, that is important to be said, we says that it is true for the current moment of time. Of course, we can modify it to put in somewhere else in the time. So here are some examples with the modifier. So this query Q makes some result, and with this modifier, we say that we want to be true for that particular moment of time, or 3 days ago, or 5 days ahead. These are some example queries. We have here, we can find the noun syntax that are on top of the hypernymy hierarchy in English with this simple query. Okay. So for the graphical user interface, this is again a simple page application. We have 3 types of queries that the user can use. It's using words, real expression, formulas. We have 2 modes in visualization of the data. One is a single mode, and the user receives what he asks for. The other one is alignment mode. The user selects 2 languages by which is used to be aligned. Let's say English and French, but the user can search for some Romanian word or Bulgarian word and to see the alignment of these syntax in English and French. Yes, this view is recursive, so starting from one object, using the relations, you can go to other objects like using the hypernymy relation or some literals, and then go to their syntax, and etc. etc. This system is fully fledged with editing possibilities. You can edit the data. You can, of course, add relations with by means of a relational wizard. This is a snapshot of the data of the system. You can see it in the previous version in production. It's quite similar in interface, and if someone is interested in the last version, I can show. Unfortunately, it's not deployed somewhere in the internet. So for the implementation, the whole system is written in JavaScript. The queries are translated into SQL. This is the more complicated part of it. Each operation makes another instance of the object in the database, so no data is lost. You cannot delete something in the database. When you try to delete something, it's marked as deleted. If you want to change the data, the data is not changed, but another instance is made with the changed data. So in this way, we can make this time machine working. We have permissions, so the users have some rights to edit some languages. Actually, every single synset have this data in which language it is. The web interface uses with the REST application programming interface service that makes the things. The user interface is in Knockout.js, and it uses Bootstrap for the interface. And for the future work, I would like to mention that we are trying to introduce another time modifiers that are with this temporal logic since and until, and their derivatives that sometime in the past and sometime in the future. And because these queries are not so easy to be written, we would like to make some query wizard that will help the linguist to write easily these queries. And that's it. Thank you.